Welcome to the presentation of the Newton-Raphson method, which is a powerful numerical tool for finding the roots of a real valued function. It is an iterative method that improves approximations of root using the function's derivative. The method is named after Isaac Newton and Joseph Raphson. Newton originally developed a similar approach in his work on polynomials, but Raphson refined and presented a clearer iterative form in 1690. Though it is commonly attributed to both, Thomas Simpson later generalized the method to more practical application. Let us briefly discuss about the geometry of this method. In earlier methods, we have seen how the secant line is used to get better approximations of the root. The Newton-Raphson method is based on the tangent line approximation. Given a function f of x, the root is estimated using the tangent to the curve at an initial guess xn. The next approximation xn plus 1 is obtained by extending the tangent to the x-axis. To understand the Newton-Raphson method, we first need to recall an important mathematical tool, Taylor's theorem. The statement of the Taylor theorem says that if f of x is a continuous function and possesses continuous derivative of order n in an interval that includes x equal to a, then in that interval f of x equal to f of a plus x minus a f prime a plus x minus a whole square divided by 2 factorial f double prime a plus etc. plus x minus a to the power n minus 1 divided by n minus 1 factorial f n minus 1th derivative at a plus a remainder term, where the remainder term is equal to 1 by n factorial x minus a to the power n f n nth derivative at psi, where psi is a real number between a and x. Now let us go through the procedure of the Newton-Raphson method step by step. Let us start with an initial approximation of the root x naught for the function f of x equal to 0. Let us assume that the actual root is x1, which is equal to x naught plus h. Now we will apply Taylor's theorem for f of x with x naught and x1. Since we assume x1 is the actual root, we have to take f of x1 equal to 0, and the difference between x1 and x0 will be equal to h. Neglecting the higher terms, we will get h is equal to minus f of x0 upon f prime x0. Then x1 will be equal to x0 minus f of x0 divided by f prime x0. This leads to the general iterative formula of the Newton-Raphson method, that is x n plus 1 will be equal to xn minus f of xn divided by f prime xn. So by repeating this process, we refine our approximations and move closer to the actual root. Now let us ask two important questions about the Newton-Raphson method. The first one is, since we are speaking about a sequence, does the sequence xn converge? If it converges, what is the rate of convergence? Understanding these aspects will help us determine the efficiency and reliability of the method. Previously in the iteration method, we have derived that xn plus 1 is equal to phi of xn, and you may recall that the sequence converges if absolute value of phi prime x is less than 1. In our case, phi of x is x minus f of x divided by f prime x. So the sequence will converge if absolute value of phi prime x, which is equal to absolute value of x minus f of x divided by f prime x, its derivative, is less than 1. By simplifying, we can say that the sequence converges if absolute value of f of x f double prime x divided by f prime x whole square is less than 1. Due to continuity, we can say that f of x, f prime x and f double prime x are bounded in the interval containing the actual root x equal to psi. If psi is a simple root, that means psi is not a repeated root, then f prime psi is not equal to 0. Then f prime psi is either positive or negative. So we can choose an epsilon such that absolute value of f prime x is greater than or equal to psi in a suitable interval. Now let us choose epsilon such that absolute value of f of x, f double prime x is less than epsilon square. Substituting everything in the previous equation or previous term, we can say that absolute value of phi prime x is less than 1. That is, the sequence will always converge. About the rate of convergence, we can prove that the Newton-Raphson process has a second order quadratic convergence. This is given as an exercise problem for you to work out. Now let us try to solve a real problem using Newton-Raphson method. Find the root of the equation x sin x plus cos x equal to 0 using Newton-Raphson method. Let us take f of x equal to x sin x plus cos x and f prime x will be equal to x cos x. Then the iteration formula xn plus 1 will be equal to xn minus xn sin xn plus cos xn upon xn cos xn. Starting with x naught as 3.1416, we will get f of xn equal to minus 1 and xn plus 1 will be 2.8233. Then replacing 3.1416 with 2.8233, we will get x2 as 2.7986 and x3 as 2.7984. Then we can say that the approximate root is 2.7984. Try to solve the following problems yourself.